For our final magma chamber simulator tutorial, we're going to look at how to interpret the output data from an MCS Trace Elements run. Let's navigate through to the input and output folder. So in the documents folder, we want to open up the MCS folder and then the input and output folder. Then find our output file, afc_tutorial.xlsx. As a reminder, this is the same output file that was generated by the MCS before, not a new one. So don't forget that your MCS phase Equilibria results are in this file too. You wouldn't want to accidentally delete them. The MCS Traces output file consists of 3 Excel worksheets that are appended to the beginning of the original MCS phase Equilibria output file. I'll zoom in here just a smidge. And there's traces1 magma, traces_1 wall rock, and traces1 output. Let's go ahead and take a look at the first tab. In a similar fashion to the MCS phase Equilibria, MCS Traces records the initial concentrations and partition coefficients used for each system, so there's no question about what you did in your run. All of that information is here in the first 6 rows of our sheet, and it's got headings that are in yellow. It's actually been quite a while since I've made the last video, so I sure don't remember off the top of my head what my specific input parameters were. But I can look up here where the headers are yellow, and I can see that my magma subsystem had an initial concentration of 92 ppm nickel and 408 ppm strontium. I can also see the mineral melt and mineral fluid partition coefficients that I assigned for each trace element and fractionated phase. If the trace element you're modeling has both an initial concentration and an isotopic ratio, so in this case strontium, you can scroll all the way to the right, get over here, to the mineral CO2 partition coefficients to find the initial isotopic value. So for example, if you wanted to model strontium, neodymium, or lead isotopes, those initial isotopic ratios for the magma subsystem get recorded here. Oxygen isotopes, they're a bit different, and that's because the MCS doesn't require an initial concentration of oxygen or any partition coefficients to be associated with it, only initial isotopic ratios, so those are recorded here in rows 5 and 6, all the way back at the beginning of the spreadsheet. The MCS Traces output data is organized and color-coded in a similar manner as the MCS phase Equilibria output data. Headings for each column of output data are here in row 8, and they're super obvious because they're in bright cyan. If we scroll down, we can see that just like with MCS, the different magmatic differentiation mechanisms are highlighted different colors. So rows with fractional crystallization steps are white. And when we scroll down, we see that rows with assimilation are in cyan. Now this run doesn't have any recharge events, but just like with the phase Equilibria, if we had a recharge event, that row would be highlighted in orange. However, unlike MCS phase Equilibria, we don't have all of the information for both subsystems in one place here. MCS Traces results in this sheet are for the magma subsystem only, and results for the wall rock subsystem are given in the next sheet, traces_1_ wall rock. And we'll get back to that one later. So the first group of columns here contains much of the same information as that run summary tab. Remember over here? And this is where those phase Equilibria outputs are recorded, the majors. So we have recorded which differentiation process is occurring, the temperatures of the magma and the wall rock subsystems respectively, and both the incremental and cumulative masses of all phases, liquids, solids, exolved fluids that are present at each temperature step in the run. And this is truly what sets the Magma Chamber Simulator Trace Elements and Isotope Calculator apart from other geochemical modeling programs. Because your trace element and isotope models are based off of these phase Equilibria results, they will be both energy and mass constrained. To the right of these parameters, MCS also reiterates the major oxide composition of the liquid at every temperature step in the run. I find this really handy because now I don't have to switch back and forth between the Traces tab and the Run Summary tab. Instead, all of the information is nicely recorded in one place. And after the magma liquid composition, the MCS Traces results are recorded to the right of this first yellow column. If we scroll down, we can see that it says Elements and Isotopes. After the yellow elements and isotopes column, we have the calculated trace element and isotopic compositions for the magma subsystem. I didn't want this tutorial to last forever and a day, which, by the way, is an excellent album by Motel Drive. If you've never listened to it, I highly recommend it. So I elected to use a small number of elements, nickel and strontium, as well as strontium and oxygen isotopes. Moral of the story, this spreadsheet has the potential to be very, very, very long, depending on how many trace elements you want to model. So the first group of columns will give us the concentration in the melt of each trace element we've modeled. In this case, nickel is first, followed by strontium. If other trace elements had been selected, you would find an additional column for each trace element appended here. And if you have also elected to model any radiogenic isotope systems, those results will be next to that particular isotope's corresponding trace element, like so. So we have 87 strontium over 86 strontium is going to be next to the strontium concentration column. And if we were to have modeled neodymium and neodymium isotopes, we would have found that 143, 144 neodymium would have been next to the neodymium column, etc., etc., etc. And we can scroll down and see that as fractional crystallization proceeds, our nickel becomes progressively more and more depleted in the melt, while the strontium depletion gets delayed until the onset of feldspar crystallization, which is pretty cool, 4 temperature steps down into the model. And as fractional crystallization is the only process occurring, the isotopic composition of the melt won't change until assimilation sets in further down here in the cyan lines. Next we have another yellow column, this time labeled M solids content. And this separates the next group of columns from the first. These columns record the concentration of each trace element modeled in each mineral phase present within the magma subsystem mineral assemblage at every temperature step within the model. I know that's a mouthful. So think of each row as a snapshot of the mineral assemblage present within the magma subsystem at any given temperature. For each of these phases present, here you can find the concentration of each trace element you have modeled. For example, as our magma subsystem cools, this system will crystallize out first 2 different clinopyroxenes, followed by plage, then a spinel, an oxide, whitlockite, apatite, and then phaeolitic olivine, way on down at the end. As these phases fractionate out, the concentrations of the trace elements change as a function of the phase equilibria constrained species and masses produced by the major element model, but also the partition coefficients and the initial trace element concentrations that you of the user has set. And when assimilation sets in, we can see that these phase assemblages are affected accordingly. These empty cells occur because that phase wasn't stable at that particular temperature step in the model. And because it can be really, really, really cumbersome to deal with all of these numbers, here in the next group of columns, we've recorded the bulk concentration of each trace element in the entire mineral assemblage. This is really nice. So we can scroll over here. The first column is going to be the total sum of all nickel in the magma cumulate phase at that particular temperature step, or the bulk instantaneous solids. The second column is going to be the total sum of all nickel in all of the magma cumulate phases up to and including that particular temperature step, or the bulk cumulative solids. And now the bulk cumulative solids, you'll notice they're not simply a running tally of the bulk instantaneous solids, and that's because we've rebalanced the proportions of each mineral phase in the cumulates as the magma cools. I can personally attest to the tedious of doing this math by hand. It's the worst. And it is really nice that these calculations have already been done for you, especially for those of you folks who may be interested in cumulative complexes. The next 2 groups of columns have to deal with the concentrations of each trace element and the exsolved fluid phases present in the magma subsystem. In the first group of columns, you'll find the instantaneous bulk concentration of each trace element in the fluid phase, so nickel first and then strontium, just like with the solid phases that fractionated out. Then in the second group of columns, the cumulative bulk concentration of each trace element has been calculated and recorded for you. The next yellow dividing column is labeled bulk solid and bulk fluid Ds. Here we've calculated the bulk solid melt distribution coefficient, as well as the bulk solid fluid distribution coefficient for each trace element you, the user, has modeled. As you can see, I didn't want any of these trace elements to partition into our exolved fluid phase, so I set those bulk solid fluid distribution coefficients for both nickel and strontium to 10,000, and they're going to remain at 10,000. But the bulk solid melt distribution coefficient is calculated by standard mass fractions, again according to the proportions of each phase is present in the mineral assemblage at that particular temperature step. So as our magma cools and crystallizes and the different phases appear and reappear or are no longer stable, our bulk solid melt distribution coefficients for each individual trace element will change accordingly. Finally, if you have chosen to include oxygen isotopes in your MCS model, as I did for this example, those results will be in the very last column in this spreadsheet. No matter how big it gets or no matter what other elements you've modeled, the Del 18O calculations will always be the last column in the spreadsheet, so that's where you can find them. We can scroll down and see that as FC proceeds, it doesn't change, but sure enough, when assimilation sets in, the assimilation of the wall rock is increasing the Del 18O value proportionally to the amount of residual melt that has been assimilated. So that's all of the information we have for the magma subsystem. But if we switch tabs over here to the traces _1_ wall rock tab, we can see that the same information is recorded for the wall rock subsystem. Let's take a closer look, and I can scroll in. The information in the spreadsheet is organized in the exact same way as the traces 1 magma spreadsheet. So again, initial concentration, partition coefficients, Del 18O values in the first 6 rows. Row 8 tells us what columns are, and then rows 10 on down give us AFC processes. So really the only difference here is that this records the state of the wall rock subsystem, and only after every AFC equilibration step has been completed. So those cyan AFC lines in the traces 1 magma spreadsheet, those have been completed, and then the state of the wall rock subsystem is going to be recorded here in this spreadsheet. The final tab, traces _1_ output, is simply the main tab where all of the information in traces 1 magma and traces 1 wall rock comes from, but it's just not in a nice and pretty easy to look at format. You're welcome to poke around in there, but there's not any new information that we haven't already looked at. So that's it. You've now finished the tutorials for the Magma Chamber Simulator. I hope that these have been helpful in getting yourself oriented to our new version of MCS. If you're in need of further assistance, you can reach the Magma Chamber Simulator Research Group via our website, and that's at mcs.geo.ucsb.edu. You can scroll down to the bottom here, and we've got links to contact either Frank Spera or Wendy Borson, our 2 fearless leaders, with any questions you may have. And as always, happy modeling!